So welcome to the Homotopy Type Theory Electronics Seminar Talks. So I'm Dan Christensen, and I'm the hottest host this week. I'm sure if your microphones weren't muted, I'd hear lots of laughter about that. So before we start, just a few announcements. Some of you may be attending for the first time, and some reminders for those who were here last time. So first of all, we do have a mailing list, so if you'd like to receive updates about the upcoming talks, you can sign up for the mailing list. The link to sign up is on the hottest webpage. Second, as you've been hearing, we've been fiddling around with the video, and we do record the talks. And subject to the speaker's approval, we upload them to YouTube. So that implicitly means if you ask questions, you will be recorded as well. Third, we want it to be very informal and interactive, so we want it to encourage questions. And the way we'll do that is you simply unmute your microphone and ask a question. Interrupt the speaker, get their attention, and then ask your question. If you forget to remute it, I may do that for you, especially if I start to hear some echoes. So then if you have a follow-up question, you might need to unmute your microphone again. And in general, please keep your microphones muted because we have had some problems with echoes if people don't have headphones on. The talk will last for about 60 minutes, and then we have room for 30 minutes of discussion after that. You should think about it as like going up to the speaker after the talk and just finding out more, or any kind of discussion like that. Okay, so before I introduce the talk, are there any questions about the procedures? Anything that I forgot to mention? No? Okay, so I will introduce today's speaker, who is Emily Riehl from Johns Hopkins University, and her title is The Synthetic Theory of Infinity Categories versus the Synthetic Theory of Infinity Categories. So please take it away, Emily.
Great, thanks. So I actually have two people here with me, and I want to quickly introduce them. So these are two of my PhD students at Johns Hopkins, Slo Klingman on there, and David Myers. So anyway, so we're also doing the thing where we've got like a massive group, and I think this is a really exciting initiative. Congratulations to the organizers for allowing us, so many of us, to be together at once. So
thank you very much. Thank you.
Yeah. Anyway, okay. Right. So first thing I want to say is what I'm talking about today is very much joint work. In fact, two joint projects. So one is with Dominic Verity, who's one of the Australian category theorists, and then the other is with Mike Shulman. I guess let's just see what the plan is. Here's the abstract. I thought if you wanted to test your resolution, I'll just sort of pause for a second. Computers look okay? Yeah?
Did you say the abstract? I don't see an abstract.
So you're still on the first slide?
Yeah.
Okay. Yeah, it says sharing is pause, bring your shared window to the front, but then when I click on resume share, nothing happens.
Okay, I'm at a loss. I mean, do you have that window as having the focus?
I'm clicking on it and stuff. So yes, I would consider it as the front.
Okay. Well,
let me just restart. You have my title slide now?
Yes.
Do you have the second?
Yes.
Okay, cool.
All right.
This was the sort of testing the resolution. Are we looking up sort of vaguely okay?
Looks good to me.
Okay, the idea for this talk came from a talk that Mike Shulman gave at the joint meetings in honor of Vladimir Voivodsky very recently on, I think it's sort of technically supposed to be computational Trinitarianism, but I'm perhaps bastardizing that a little bit and calling it some sort of homotopical Trinitarianism. A way to present it is that these different vertices. There's mathematics that might have a homotopical, the study of mathematical objects that have some sort of homotopical content, the natural home in which these objects live, which are some sort of higher categories, and homotopy type theory, which is this new foundation system that, from my point of view, is sort of particularly apposite for studying this type of mathematical object. So kind of a standard relationship between these different perspectives on homotopy theory is you could take your homotopical mathematics and formalize it in homotopy type theory, and then interpret that homotopy type theory in suitably structured higher categories. Or you could sort of directly internalize the homotopical mathematical constructions, or the homotopical mathematical objects, and you have some sort of relationship like this. But from the point of view of developing a synthetic approach to a mathematical theory, we're kind of traversing this triangle in another way. So again, to start, you have some sort of mathematical object with a homotopical flavor, which is on the top. You can consider the category of structures like that, which will again be some sort of higher category. Then think about its internal logic, which you might describe syntactically using something like homotopy type theory. And then this is giving you sort of a synthetic way of viewing the original mathematical object. So, so synthetic homotopy theory can be understood as sort of tracing around this triangle, I guess, clockwise, starting from the top. So here we have some sort of notion of homotopy type or infinity groupoid. One categorical model of this is the category of simplicial sets, maybe specifically complexes in simplicial sets. And this model inspired some of the axioms of homotopy type theory, which is now can be described as a synthetic theory of homotopy types, where one of its aspects is a synthetic theory of homotopy types. So Mike and I have recently sort of reproduced this story with the aim of describing not infinity groupoids, but infinity categories, which I'll define in a second, but these are sort of infinity one categories. So they have some sort of non-invertible morphisms at the bottom level, but invertible all the way up. So here there are many categorical models. Again, one category of these things are called rest spaces. And the internal logic of rest spaces motivated our augmentation of homotopy type theory. It's something that Mike refers to as simplicial hot. And this gives us a synthetic approach to developing the theory of infinity categories. So one of the things I want to talk about today is what this looks like with a specific aspect of the theory of infinity categories, namely the theory of adjunctions between infinity categories. But what's interesting about this tale of the development of synthetic infinity category theory is I've also worked on this in a second guise. So another categorical model of infinity categories is something called quasi categories. And with Dominic Verity, we have axiomatized the properties of the category of quasi-categories into something that we call an infinity cosmos. And then working in an infinity cosmos, we're developing a theory, the theory of infinity categories in a way that's more synthetic than the sort of classical approach, which is just directly in the categorical, quasi-categorical model. And I would describe as analytic because it's the definitions and the proofs are very specific to the combinatorics of that model. So the plan for today is to compare these two. So talk about the synthetic theory of infinity categories and then talk again about the synthetic theory of infinity categories. So I mean, more precisely, first I'm going to say a little bit about what do I mean when I'm talking about infinity categories. How do most mathematicians understand infinity categories? Then I'm going to describe a little bit of how the synthetic theory is set up in my joint work with Verity. So this is through this notion of an infinity cosmos, which is inspired by the quasi-categorical model of infinity categories. And we'll talk about adjunctions and then homotopy coherent adjunctions in that context. And then I'm going to restart this discussion looking at another approach to the synthetic theory of infinity categories, which is based on this augmentation of homotopy type theory that Mike has developed, which allows us to talk about simplices and use them to parameterize these internal categorical structures. And we'll again define adjunctions and then talk about homotopy coherent adjunctions. And then at the end, I'm hoping we'd have some sort of discussion about synthetic approaches to mathematics in general. And I have a few comments, but I'm hoping that most of the discussion will be involve you all. So, okay, any questions before I go on? Okay, right. So let's start about semantics. So what are infinity categories? So infinity categories. Firstly, it's a nickname that not everybody likes, but it's a nickname that I'd say Jacob Lurie popularized. He was one of the key figures, along with Andre Riehl, in the development of the analytic theory of infinity one categories. So really proving that ordinary category theory extends to infinity one categories. So, and what the idea of an infinity one category, so that's the proper name, but I am going to follow convention and refer to them just as infinity category because it's shorter. So the idea is that some category where between the objects we don't just have a set of arrows, but we have some homotopy type. So the ordinary maps between objects might be the points in this topological space or homotopy type, and then it's a category that's somehow weakly enriched over these homotopy types, or weakly enriched over spaces. And the weak is important here because in examples, constructing a strict enrichment is not always practicable. So schematically, what we mean is an infinity category is something that should have objects and arrows between those objects, which I'll give a dimension now. We'll say these are sort of the one arrows, the ordinary arrows. And, you know, like an ordinary category, we have composites of one arrows. You know, one of the axioms is you can always compose composable pairs of arrows. But here we think of this composition, rather than being a unique operation, a strict operation, as something that's witnessed by an arrow in a higher dimension, and that arrow is required to be invertible. So, and this composition then is associative, but I mean, since it's not even sort of uniquely defined, it's also not uniquely associative. The witness here is an arrow in dimension 3, and it's witnessing the associativity both of the composite, but also some sort of coherence condition on the witnesses of the binary compositions. And this witness, this associativity witness, is also an invertible arrow. And then we have data in dimensions 2 and 3 now, and that needs to be coherent all the way up to higher invertible arrows. So that's sort of the schematic idea. The reason this is called infinity one is, you know, we have arrows in all dimensions. We have 1 arrows, 2 arrows, 3 arrows, 4 arrows, and above dimension 1, they are invertible. So there are more general notions of higher category that have more dimensions of non-invertible arrows, but we're not going to talk about that today. Okay, so the problem with this definition is it's not very precise. I haven't specified sort of the boundary data of a 3 arrow, for instance. There's different choices that you could make there for what sort of the shapes of these arrows. I haven't explained this sort of weak enrichment or this weak composition. I haven't really talked about units. So, okay, so the notion of infinity one category is made precise in a variety of models of infinity. Again, I'm just going to call them infinity categories now. So there are a variety of well-known models of infinity categories. So the easiest to describe are things called topological categories or relative categories. So topological category is just a category that is strictly enriched over topological spaces. So it's got objects and then Hom spaces and a continuous composition function that's associative on the nose. So it's very easy to understand. A relative category is just an ordinary strict one category with some class of maps that we're calling weak equivalences. The idea is we should sort of pretend those have been inverted somehow. So those are really easy to understand. The challenge is the corresponding maps in both of those models aren't really the right notion of functor between infinity categories. They're too strict somehow, so we don't sort of see all of the homotopy coherent functors, which are the maps that we want. So from my point of view, those models are less useful because when you're developing the theory of the categories, the functors are hugely important, and I want them to be just the morphisms in the category where the model lives. So I'm going to ignore those 2 vertices. So quasi-categories are one of the oldest models. These were originally called weak Kahn complexes by Boardman and Vogt. So it's a simplicial set satisfying some condition. And these are going to feature sort of implicitly, because this is sort of the inspiration for the first synthetic approach to infinity categories that I'll discuss, which is joint with Verity. And then the Rusk spaces, which are originally called complete Siegel spaces. This is another pre-sheaf model of infinity one category due to Charles Rusk. And these are the basis for the synthetic theory of infinity categories joint with Mike Shulman, because they interact well with a known model of homotopy type theory, which isn't the case for the quasi categories. The other two things the other two vertices of this diagram that I've not mentioned, the Siegel spaces or one complicial sets will fall under the purview of the first synthetic approach to infinity categories. So that's why they're mentioned here. Okay, so let's just sort of dive right in. So the way the first synthetic theory of infinity categories works is we look at this quasi-categorical model, which is the most successful. More theorems are known about quasi-categories than about any other model of infinity categories. And an infinity cosmos is an axiomatization of the property of this category of quasi-categories. So it's of the I usually say the universe in which infinity categories live as objects, but I shouldn't say universe to this audience. So pretend I didn't say that. Okay, so I mean the category of quasi-categories has objects which are quasi-categories. That's what I mean by saying it's the category of quasi-categories. It has functors between them, and these functors are the points of a Hom quasi-category, which is traditionally denoted by fun A, B. So this is, the category of quasi-categories is Cartesian closed, it's enriched over itself. That's what I'm saying here. And there's also a specified class of isofibrations, which I've told you they're fibrations, and so they have the closure properties you'd expect: stable under pullback, stable under inverse limit of towers, so on and so forth. And then if I form certain limits of diagrams of quasi-categories of isofibrations, I get a quasi-category back. Now there's a very precise way to describe the class of limits that will have this property that I don't really want to get into, but I can do various sort of homotopy limit-like constructions involving quasi-categories and isofibrations, and I stay in this category of quasi-categories. So what an infinity cosmos is it's just all of these properties, again, where I replace the quasi-category with infinity category in sort of all but one place. So I guess in practice, so many infinity cosmoi are Cartesian closed, so enriched over themselves, but not all of them are. And if something is sort of enriched over quasi-categories, that's also extremely useful. So again, an infinity cosmos is some sort of category which has objects, which are the infinity categories in that particular model. The arrows are what we'll call functors between infinity categories, and these are actually the vertices of some quasi-category of arrows, so we'll have access to higher dimensional arrows as well. We have some special class of fibrations, and then we can do various limit constructions. That's the idea. And there are a bunch of examples. So the four good models that I mentioned on the previous page are all infinity cosmoi. So what this means is, working from the axioms of an infinity cosmos, I can talk about infinity categories as modeled by quasi-categories, or by complete Siegel spaces, or by Siegel categories, or by one complicial sets, and I won't ever need to distinguish between those models. What I'm talking about will apply to all of those models. Okay. Questions so far? Is this? Okay. I can't see anybody anyway, so this feels silly. Maybe I'll just would you please interrupt me at any point if I'm saying something that doesn't make sense. How about that? So, okay. So, and in fact,
I'm sorry. Can I ask a question?
Please. Yeah.
So the infinity cosmos, what kind of object is it to which these properties apply?
So it's I'm sorry.
Yeah, no, that's the question. Yeah.
Great. So it's a simplically enriched category, and you should think of it as being very large. So it's a yeah, and I mean sort of simplically enriched in a strict sense. So this is meant to be like the infinity 2 category, where infinity 1 categories live as objects. So the definition is it's a category that is strictly enriched over simplicial sets, but in which those Hom objects are all quasi-categories. And then I have a specified class of maps that I'm calling isofibrations, and then I ask that various limits exist in these simplicially enriched sets. But actually, for most of this talk, we're going to get away with quite a lot less than that. So one of the first things you can prove about an infinity cosmos is it has a quotient, which is a strict 2 category, whose objects are the infinity categories in that cosmos, whose 1 cells are the functors in that cosmos. These were the vertices of these mapping quasi-categories. And now we have 2 cells, which we might as well call infinity natural transformations because they're the things between infinity functors. And the definition of this is sort of non-obvious a priori, but a posteriori, I think it is clearly a good notion. So these are homotopy classes of 1 simplices in these mapping quasi-categories. But it doesn't matter where they come from. So the point is now I have infinity categories, infinity functors, and infinity natural transformations, and these form a 2 category, which means I can work with them like I work with ordinary categories, ordinary functors, and ordinary natural transformations. I have access to the same sorts of composition operations. Okay, and there's a result that indicates that morally this is the right, or this is an appropriate context in which to develop the theory of infinity categories. So in each of the models, the quasi-categories, the Resk spaces, the Siegel categories, and so on, there's a well-known notion of equivalence between infinity categories. Also, in any 2 category, there's a standard notion of equivalence. This will look familiar to you all. It's a pair of objects. It's a pair of morphisms that go in opposite directions, and then we have a invertible 2-cell invertible natural transformation comparing the composites to the identities. And the result is that that 2 categorical notion of equivalence precisely captures the notion of equivalence that whoever developed this model had in mind already. So if we're doing equivalence invariant 2 category theory, we're doing an equivalence invariant infinity category theory is the point. So, okay. So what's nice about this setup is there's quite a lot that I know about adjunctions in any 2 category. And just by specializing those results now, there's quite a lot we know about adjunctions between infinity categories. So the standard 2 categorical definition of adjunction says if you're working in some 2 category, like this 2 category of infinity categories, infinity functors, infinity natural transformations, the data of an adjunction is just the pair of categories, the pair of functors, a pair of natural transformations that have source and target as I've specified, and then there needs to be some sort of composition relations relating eta and epsilon. These are called the unit and the co-unit of the adjunction, and they have to satisfy some rules. And if you can't read these diagrams, it doesn't matter. There's some sort of condition satisfied by the composition. We'll study that condition a little later on when we're talking about homotopy coherence. So anyway, so there's a standard definition of adjunction that works in any 2 category. And then if you ask your favorite 2 category theorists, pick a 2 category theorist off the street, there are these results that they would be able to prove because these proofs work in any 2 category. And so now we have these propositions about adjunctions between infinity categories. So one is that they can compose, the other is about uniqueness of adjoint functors, and then there's this kind of cute result that ends up being really important, that if you have an equivalence, you can make that into an equivalence that's also an adjunction, which is useful for various technical things. Okay, so this is sort of the 2 category theory of adjunctions. These are sort of very standard, relatively straightforward things. But there's we haven't really talked about the universal property of an adjunction, and the vehicle to do that makes use of some of these limit constructions in the infinity cosmos. So any infinity category has an infinity category of arrows, which is some sort of isofibration over, there's a source and target isofibration, and it's equipped with some 2-cell that we refer to as the generic arrow. And you can reindex into this construction. So I can pull back to sort of substitute something into the source and target. And now I have a new characterization of adjunctions, which says that I have an adjunction sort of if and only if, when I look at these infinity categories of arrows and sort of reindex in this particular way, sort of maps out of the left adjoint are equivalent to maps into the right adjoint over the source and target evaluation. So this is the transposing style definition of an adjunction that you might be familiar with. And I can also talk about the universal property that's enjoyed by the unit and the co-unit. So if I look at a component of the unit at an element of B as at an object inside the infinity category B, I can say that's initial in one of these HOMs, and dually the co-unit component is terminal in one of these HOMs. So these are theorems you may or may not recognize from ordinary one category theory. We have them here as well. Okay, so what I want to talk about now, I mean, so I'm teaching a course on infinity categories at Johns Hopkins this fall, and when I gave this definition, my students were pretty unhappy. They're like, why is this the right notion of an adjunction? Because, you know, an infinity category is something that has kind of objects and morphisms, and then all these invertible cells sort of all the way up. It's got data in infinitely many dimensions, and somehow I've sort of truncated and forgotten about all this higher dimensional stuff and just defined adjunctions the way that you would for ordinary one categories, which have no higher dimensionality. So that seems really weird. The justification is actually we can build back up all of this higher homotopy coherence data. So let me kind of sketch a little bit about that. So firstly, a little bit more classical two-category theory. So there's a notion of a free adjunction. So it's some two category so that two functors out of that two category pick out adjunctions in whatever two category you're mapping into. So I've drawn a picture of this adj, which is this free adjunction. Has two objects, which we call plus and minus, and then it has these HOM categories, which are built from delta, delta being, I guess delta plus being the category of finite ordinals and order preserving maps. So if you know about delta, you can interpret that. If not, I mean, the sort of diagrams that you can freely build from adjunction data look like this. So, in the first diagram, this is a augmented co-simplicial object in one of the HOM categories of the two category K. We've got a bunch of endofunctors of the object on which the monad lives. So we have the identity on that object. UF is an endofunctor, UF is an endofunctor. And then there are these various two cells between these endofunctors that are built out of the unit and the co-unit. And so in the free adjunction, all that stuff is in there as one cells and two cells. And then the second picture is what in the HOM category from A to B in the notation I had on the previous slide, I have the functor U and also the functor UFU and the functor UFU and these various two cells between them, and they satisfy some relations because of the triangle equalities and because of sort of naturality or something. So, okay, so this is a thing that some people know about. What Dom and I did is we introduced what a homotopy coherent version of this would mean. So an infinity cosmos, remember, it has objects, and then between objects we have some infinity one categories, some quasi categories. So we have access to the one cells and two cells like before, but then all these higher dimensional cells. I mean, this definition is kind of too cute. We just say it's a simplicial functor whose domain is the same adj. So there's this trick where I can identify a category with its nerve, which is a simplicial set. The category has sort of objects and arrows. The nerve has in dimension 0 those objects, in dimension 1 those arrows, and then in dimension 2 composable pairs of arrows, and in dimension 3 composable triples of arrows. And somehow if you map out of one of these, you automatically get a homotopy coherent diagram. This is like part of the magic of quasi categories, which I realize will be totally mysterious to many of you, and I apologize for that. But anyway, if I just sort of pretend this two categories instead a simplically enriched category by identifying the HOM categories, these deltas with their nerves, the claim is that it parameterizes some sort of homotopy coherent diagram. So there's a lot that's needed to justify that claim that I don't have time to get into. So this simplicial category is free or cofibrant in a suitable sense, which is not at all obvious from the definition I'm giving now. And that's kind of the sense in which this is a good construction. But anyway, so the point is, what I drew on the previous slide are some of on the bottom, these are diagrams that live in these HOM categories from B to B or from A to B. So now I'm just extending that data of those diagrams to homotopy coherent diagrams. So there's some sort of higher dimensional invertible cells that are part of the data whenever I have a composable pair of arrows. So that's the notion of homotopy coherent adjunction. That's a sketch of the notion of homotopy coherent adjunction. So what is this higher dimensional adjunction data? So again, inside one of these HOMs between two objects, I have as vertices the one arrows, so things like F and U. And then as the morphisms in the next dimension up, I have these things that were the natural transformations. So this is the eta and the epsilon, the unit and the co-unit, and also whiskered composites of that. And then I can have also data that are correspond to 2 simplices and 3 simplices and 4 simplices and sort of all the way up. So in a homotopy coherent adjunction, there is specified witnesses to the 2 triangle equalities. These were the coherence conditions relating the composites of eta and epsilon, the unit and the co-unit. And then I also have 3 simplices and 4 simplices and 5 simplices and all the way up. And so what I've drawn for you is a pair of 3 simplices, which we're calling omega and tau for sort of no particular reason. So I've drawn these 3 simplices as thinking of them as sort of a transformation from a pasted composite of 2 of the faces to another pasted composite of 2 of the faces. But I mean, that's just because I'm trying to draw a 3-dimensional object in 2 dimensions. It's really, this inhabits a tetrahedron. That's kind of the right way to visualize these 3 simplices. So, so what this data includes is firstly the data of a new 2 simplex, which is mu, which appears on the right-hand side of both of the 3 simplices that I've drawn. And what mu is it's some sort of extra coherence condition that witnesses that if I take F eta U and I compose it with this thing that I'm calling epsilon epsilon, that's a horizontal composite of 2 of the co-units, then I should get the co-unit. So that's a relation you can prove from an adjunction, but it's maybe not one of the ones that you'd think of. It's sort of a higher relation. And so in a homotopy coherent adjunction, there's some data that is a specified witness for that. And you'll notice that data appears as a face of both of these 3 simplices. So part of the coherence condition is that I can pick a 2 simplex that witnesses that composition relation once, and then that will appear as faces of, these 2 higher dimensional simplices, but also many, 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 many other higher dimensional simplices as well. The data of a homotopy coherent adjunction is infinite, so there's kind of a lot of coherence conditions going on here that I swept under the rug in this very compact definition. Okay, so it seems crazy that like this sort of rigid structure would exist, but it does, otherwise I wouldn't be talking about it. So this is one of the main theorems that Dom and I prove in sort of our second paper in the series on the synthetic theory of infinity categories. And I wanted to give a little bit of a sketch of the proof because we'll revisit some of these ideas when I talk about the other approach to the synthetic theory. So if I have the data of an adjunction, as I first defined it, just an adjunction in the 2 category, what that gives me is a pair of infinity categories A and B, a pair of functors F and U, a pair of natural transformations eta and epsilon, that's the unit and the co-unit, and then they had to satisfy some relation. So in particular, that means there is a witness to these composition relations. So this is this alpha and this beta. I didn't name the witnesses before, but I am now, as I picked 2 arbitrarily. And so now from the data that I've just specified, I can forget some of it. Once I know it exists, I'm going to forget the data down to either just the pair of functors and the unit, or the pair of functors, the unit, the co-unit, and one of these 2 witnesses. And then using the universal property of the unit that I mentioned, that its components are initial in some HOM, I can then extend all the way up. I can generate all of this coherence data. So this is a very detailed analysis of the simplicial category adj as a cofibrant simplicial category that we definitely don't have time to get into. But that's kind of the sketch of how this goes. And sort of moreover, the choices of this data of a homotopy coherent adjunction are not unique, but there's some space in which sort of all of the data of the homotopy coherent adjunction lives as a vertex, and these spaces are contractible. So, okay, so that's a pretty good theory, I guess. Okay, that's the end of synthetic theory 1. Maybe I'll pause for a second before we start all over. So let's now maybe do something a little friendlier. Let's talk about what this looks like in homotopy type theory. So, the sort of synthetic theory of infinity categories in homotopy type theory has semantics in one of these models of infinity categories that I mentioned previously, but it's a different intended model. These are what we're calling RESC spaces. And just for some orientation, here's where these things live. So we have some pre-sheaf category. Inside the pre-sheaf category, there's a category of fibrant objects. These are Reedy fibrant bisimplicial sets, whatever that means. And Mike Shulman has proven that there's a model of homotopy type theory with all of the usual constructors and a univalent universe in as Reedy fibrant bisimplicial sets. So what was exciting to us about this particular model is inside it, we can identify types with composition. So there's a classic homotopy theory name for these, which are Siegel spaces. So we're going to call these Siegel types. And then among the Siegel types, we can identify those types with composition that also have a univalence axiom that I'll describe in a second. And these are the RESC types, and this is one of these models of infinity categories. So it's the infinity cosmos, I guess I can say now. So there's an infinity cosmos, a framework to do the synthetic theory of infinity categories that sits inside a model of homotopy type theory. So the idea was using this model to sort of describe the internal language, develop a type theory that allows us then to improve theorems about infinity categories that will then be valid in this model. So, okay, so, and just for orientation purposes, so in this bisimplicial sets model, there is a type which parameterized paths inside the given type, so there's sort of an interval, but there's also a directed interval type, which I'm using categorical notation for. That's 2 with a blackboard bold is like the category with 2 objects, 0 and 1, and 1 non-identity morphism. So, okay. So in homotopy type theory, we're pretty familiar with the interpretation of identity types. So an identity type depends on 2 terms in the same type, and then a term in the identity type is interpreted as a path. So in our simplicial version of homotopy type theory, we're also going to have something called a hom type, which, like the identity type, depends on 2 terms in a given type. But we're interpreting a term in a hom type now as an arrow from X to Y, a directed arrow. So there's no, having an arrow from X to Y does not guarantee you an arrow from Y to X. These are non-invertible. So in the type theory, we axiomatize simplices and a construction of an extension type. So our types are allowed to depend on simplices. This is kind of like the cubical approaches to type theory. And then we're allowed to form extensions of a map sort of from a sub bit of a simplex into a type to a map from the full simplex into type, and that's where these homs come from. So I don't really want to focus on the internal mechanics of the simplicial type theory today, so I'm just going to hope you'll let me write hom and start using it. So, but we've already seen this before. So semantically, these hom types, which we're interpreting again as the types of arrows between 2 terms in a given type, these recover this sort of infinity category of arrows that I mentioned in the first approach to the synthetic theory when we're talking about sort of the transposing definition of adjunctions. So, okay, so let me, in this approach to synthetic infinity category theory, we have types, and then some types are Siegel, which have composition, and then some types are RESC, and those are really the infinity categories. So the quick definition of what a Siegel type is it said every composable pair of arrows should have a unique composite, where unique is in the sense of homotopy type theory. So it means it's a contractible type that witnesses composition. So, so again, there's some sort of extension type construction that says that that would give the data of a composition and a witness for the composition. And so the Siegel condition says that should be contractible. Then a Siegel type is RESC if every isomorphism is an identity. So from just the definition about unique composition, which I gave you, you can prove that composition is also associative, and there exist these identity arrows that are unital for composition. So I have a categorical structure. And now I can define an isomorphism in a Siegel type to be a arrow from X to Y, for which there exists an arrow from maybe a left and a right inverse. That would be a type of isomorphism. So, well, I guess here's the type of isomorphisms. So there's a map using a kind of I guess path induction induces a map that converts a path to an isomorphism, and the rest condition says that every isomorphism is an identity, so comes from one of these paths. And then finally, this isn't really going to feature today, but I thought I would mention it. So we have a notion of when a type is discrete, and that's the case in which every arrow is an identity. So among the infinity categories that we're studying in this synthetic theory are the infinity groupoids, which are the, using the sort of higher categorical structure of the identity type. So this is a result that you're maybe more familiar with, is how to think about paths and paths between paths and paths between paths and so on as some sort of infinity groupoid. So the infinity categories, the RESC types in which all of the arrows are isomorphisms, recover this structure. So, okay, so now I'm going to try and build the theory of adjunctions between infinity categories. And there are going to be a lot of parallels that you'll notice between the first approach to the synthetic theory of adjunctions between infinity categories. So the first thing to note is we have something like a 2-category of Siegel types. So these are just types with composition and maps between them and so on. So the first observation is that you have a function type in homotopy type theory, and a term of that function type sort of automatically is a functor. So it preserves the composition and preserves the identities. So therefore we can interpret this type of functors as a Siegel, as we can interpret this function type as a type of functors. Sorry, somebody said something.
Yeah, just on the last definition of a res type, just for clarity, right? There's a relationship that one can state between res types and univalence, right? Like if every type is res, then you're univalent or something. Is that correct?
So the RESC condition, which is that this map from id to iso is an equivalence, is kind of a local univalence condition, I guess, is what I would say. So it's, yeah.
Okay, that's it, thanks.
Great. Okay, so again, there's something like a 2-category theory, 2-category of Siegel types, these types of composition. So the first observation is any function between Siegel types should be thought of as a functor. It's preserving this categorical structure automatically. And then if I have a pair of functors, both from A to B, I guess there's an equivalence between the hom in the type of functors between these two terms and sort of the components of it. So we're thinking about terms here as natural. I don't know where that space came from. We're thinking about terms in here as natural transformations. And you can then prove that they are natural in the sense of there's some commutative square involving a component of a natural transformation and an arrow in A. And can be composed vertically and horizontally, up to sort of the typal equality. So you can find witnesses in the appropriate identity types that these composition relations hold. So, we have something like a 2-category. I don't know what a 2-category is where your equations are up to typal equality, but we have something like that. That would actually be a great thing to talk about later. So if you have a sense of what that is, tell me after the talk. Okay, so now let's talk about adjunction data. What is the definition of an adjunction between these sort of Siegel types? So again, it should consist of a pair of types. It should consist of a pair of functors. Those are, again, just terms in the function type, the usual function type. And then a pair of natural transformations, which are terms in the hom types of these function types. And then witnesses to the triangle equalities. So some sort of data that witnesses these composition relations hold. Mike came up with the name quasi-diagrammatic because we're paralleling some of the terminology for incoherent notions of equivalence. Or another notion of adjunction is a transposing adjunction between types. So this is something, again, it's a pair of functors, and then I have some equivalences that say there's a typo here. There's some sort of equivalence that says that homs in A from F to something correspondent homs in B from B to U of that something. Okay, but there's sort of something incoherent about the definition of quasi-diagrammatic. So I'm modifying this to make it sort of similarly incoherent. So if I use an incoherent notion of equivalence between types, so if I regard this equivalence that's part of the displayed equation as a map from hom A FBA to hom B B UA, together with a map going backwards, together with witnesses to both of that these are left and right inverses. So that's using sort of the incoherent notion of equivalence. We can call this data a quasi-transposing adjunction, and the point of doing so is now there is an equivalence of types between the type of quasi-transposing adjunctions, so this sort of incoherent basic adjunction data, and the type of quasi-diagrammatic adjunctions. Okay. So we might also be interested in coherent adjunction data. So, so there's a notion of a half adjoint diagrammatic adjunction that was kind of too big to fit on a slide, but what it is we start with the notion of quasi-diagrammatic adjunction that we had on the top. So I have this pair of types, pair of Siegel types. Well, eventually there'll be, pair of types a priori. A pair of functors, one going one way, one going the other way. A pair of natural transformations, witnesses, alpha and beta, to the two triangle equalities. So these could be interpreted in the simplicial type theory as two simplices whose boundary one simplices are the sort of natural transformations that are indicated there. And then also a pair of a new two simplex, which is this mu that appears on the right-hand side of both triangles, and a pair of three simplices, which are this omega and this tau. And this is exactly the same diagram you saw before. So, I mean, the reason that we thought of this definition is sort of inspired by the corresponding theorem about homotopy coherent adjunctions that I'd proven already with Dom. Okay, and the interest in this particular list of data is it's now something that's equivalent to the type of transposing adjunctions, which made use of a coherent equivalence between a coherent transposing equivalence. So, so use where the type of there exists an equivalence is one of these mere propositions, not some type with non-trivial higher dimensional structure. Okay, so one way to think about this sort of coherent notion of adjunction is using this half adjoint diagrammatic adjunction. And using these coherent types of adjunction data, we also have uniqueness results. So if I have, again, a pair of types A and B, a pair of functors U and F, and a unit, so that's a natural transformation from the identity to UF, and I know that it's a unit. I know that there does exist an extension to some sort of adjunction data, then that adjunction is uniquely determined. So the theorem is, again, given these Siegel types A and B, this pair of functors, and this natural transformation, there are equivalent types, and moreover, they're mere propositions. So the first type is the type of data that extends the stuff that I listed, this F, U, and eta, to a half adjoint diagrammatic adjunction. So to do so, I'm picking a co-unit epsilon, witnesses alpha and beta to the two triangle equalities, this weird two simplex mu, and then these three simplices that are some sort of coherent condition. Or I could just say, I could do a propositional truncation of the stuff that extends this just to enough data that tells me that I do have an adjunction in the two categorical sense. Or I could start with the data of a quasi-diagrammatic adjunction, forget one of the two triangle equality witnesses. So I'm leaving out alpha, but I'm keeping the other one. And then again, it's a mere proposition to extend that back to the data of a half adjoint diagrammatic adjunction, and so on. Okay, so I haven't, I mean, this is all about Siegel types, which are these types of composition. I haven't mentioned the univalence, the local univalence condition, is sort of rest completeness. And where that comes in is that allows us to convert natural isomorphisms into identities. So there it makes adjoints, you know, literally unique, not just unique up to isomorphism. So if one form of that theorem is if I'm given a Siegel type B and a rest type A and a functor from A to B, so the following types are equivalent propositions. So, so I'm looking here for a left adjoint. So the first type is the type of transposing left adjoints of U. So an F, so that then there exists an equivalence that converts arrows out of F to arrows into U, or the type of half adjoint diagrammatic left adjoints, or the propositional truncation of this type of quasi diagrammatic left adjoints of U. So again, I have some equivalences of types, but you know, there's something more in asserting that these types are propositions and not just general types. Okay, so I have a few closing thoughts, but maybe I'll pause first.
I guess you're waiting for a question. I've got one, which is, this went very fast. And
Yeah.
so in both cases, you built up to these theorems about adjoints, and that was sort of where you took us. And I guess implicit is then you said with these theorems about adjoints, then you can do a lot of the things that one wants to do. And that's in the papers, but you didn't have time to walk us through that, right? That just to state sort of clearly, that's why you built up to exactly this point, is once you have this with these uniqueness properties, then that's the tool you need to do the next steps.
Right. So, I mean, right. So I guess the question is sort of, what is all this for? Fair enough. So in the synthetic theory of infinity categories, using these infinity cosmos techniques. So the first approach that I talked about, you know, adjunctions are sort of one of the first things that we develop. And then, you know, there's, we study the relationship between adjunctions and the notion of limits and colimits and so on and so forth. And there's a lot of, so there's a lot of category theory that's built on the concept of an adjunction. So I don't see any obstacle to having adjunctions play a similar role in the synthetic theory of infinity categories in this simplicial version of homotopy type theory, but that these results are much newer, and so we haven't really pursued much in way of applications yet. You know, the interest in homotopy coherent adjunctions isn't as clear to me, except for the sort of obvious aesthetic interests, which I don't think I conveyed sufficiently, because usually I spend an entire hour just explaining what a homotopy coherent adjunction is, and I didn't want to do that today. But you know, I think, I think it's sort of an intrinsically interesting question, you know, what sort of data associated to an adjunction can be made coherent. So, and in a homotopically unique way. And so, I don't know. I mean, so I think that theory is really nice, and it's interesting that we have it proven, you know, in vaguely similar ways in these two contexts. What it's good for is not at all clear to me, but so. Does that sort of answer your question?
Yeah, that's perfect. Thanks.
Okay. Cool. So let me, I really want to stop talking and hear related thoughts about synthetic mathematics. So let me just quickly mention some observations in comparing these two approaches to the theory of infinity categories. So So, I mean, in an infinity cosmos, one of the propositions I mentioned describing the universal property of adjunctions is that we prove that there exists, this sort of basic adjunction data, which in the homotopy type theory context, I called the quasi-diagrammatic adjunction. So that's, again, the data of both adjoints and the unit and the co-unit and witnesses to the triangle equalities. So we prove in an infinity cosmos that if that data exists, then I get this transposing equivalence between these Hom types. But in simplicial homotopy type theory, we prove something stronger, which is that the types of such data are equivalent, which is more precise information, though to be honest, it's not entirely clear to me what that is. So that's one point of difference. I mean, that's not really a question you ask in classical mathematics, is sort of, what is the structure on the witnesses to the truth of some proposition. I mean, that's sort of a type theory thing that I wasn't attentive to before joining this community. So another difference between the synthetic approaches just has to do with kind of what we have axiomatized. So the infinity cosmos of RESC, the objects in that, the infinity categories in that are really just these RESC spaces. So we don't see the Siegel spaces or the ordinary types, which are these sort of redefibrant bisimplicial sets, just again, because we haven't axiomatized for that. And one of the things that was interesting to me in working with Mike is how much of the theory of something like infinity one categories doesn't need the RESC condition. I know that there are some users of infinity one category theory who like to work with Siegel spaces that are not necessarily complete, so are interested in results in this flavor. And I was kind of surprised about how much we can prove in the absence of the RESC condition. So that was something that was interesting to me. Once you've proven synthetic theorems, you want to be able to interpret them in other mathematical contexts and then conclude that you've proven something in these special cases. And from my experience, it seems to be easier to produce an infinity cosmos than to define a model of simplicial hot. I mean, because an infinity cosmos is a category with some properties, and there's lots of categories in the world, and there's and universal properties aren't maybe so hard to find, but to model homotopy type theory, you just require so much more in terms of coherence and up to strict choices and so on. So that does seem to be a point of difference. But I mean, really, my main observation is that this is very similar. These two approaches feel very similar. And I think also sort of superior to analytic or kind of classical approaches to study infinity category theory. So I'm very attracted to both approaches for synthetic mathematics. And again, I don't know if I understand why all the ideas from one approach seem to translate to the other approach. So if somebody has a sense of that, I'd love to hear it. So I'll end with some references, and thanks very much for your attention.
Okay, thank you. Let's first have some applause for Emily. Okay, I'm live, right? Yeah, so now we'll open the floor to just general questions or to more discussion type questions, anything people would like.
Okay, maybe
that's a general question.
Yeah, sorry, we have a local question, so yeah, why don't you?
Hi. Is there a universe in your approach with Mike Shulman, and is it univalent? Is it a RESC type?
Right. Yeah, so that's a great question. So one of the MRC groups was looking in part on universes in the simplicial type theory. And, a priori, there's lots of different ways to define a universe, because the terms could be sort of all types or Siegel types or RESC types or discrete types. There's various different choices. So, so semantically, there are things that are known about universes in the bisimplicial sets model, and Christian Settler has proven a lot of facts about a universe that whose terms are the discrete types and whose sort of universal fibration is modeling something called a covariant fibration, which is the sort of discrete left fibration, which I didn't talk about at all in this talk. So, I mean, some of that work is still being done. None of this is out on the archive yet, but Christian's figured out a lot of things. So, yeah.
I think there was another question.
Yes, hi. So I was wondering, in the definition of an infinity cosmos, the function, rather the functors between two infinity categories were specified to be a quasi-category. And I was wondering if that could be replaced by some other model, or perhaps the model being described by the cosmos you're working in.
Yeah, that's a great question. Right. So, and the definition of an infinity cosmos, again, is it's kind of an infinity 2 category. So it's a category that's enriched over infinity 1 categories. And for concreteness, we choose a particular model of infinity 1 categories, namely quasi-categories. So why did we choose that model? I mean, one, we wanted something really concrete, and the quasi-category model is very simple. It requires relatively little data. A lot of theorems were known about that. And then also there's the sort of via the Yaneda lemma, we get to import a lot of the theory of quasi-categories into a general infinity cosmos. So let me say just a little bit about that. I mean, limits or co-limits in a general 1 category are sort of ultimately defined in terms of limits in the category of sets. So they represent, a limit or a co-limit is defined as something that represents a particular set-valued functor that's defined using that same limit or co-limit construction. And so in particular, if you want to prove things like any limit can be computed as a equalizer of two maps between products, you can actually prove these theorems at set and then apply the Yaneda lemma to get it in any 1 category. So similarly, and occasionally we do use stuff about quasi-categories and then generalize it into an infinity cosmos using those techniques. So that's one reason for it, but it's not really an essential choice. So one thing to say is that the 4 infinity cosmoi that I mentioned, the quasi-categories, Resk spaces, Siegel categories, and 1 complicial sets, those are all Cartesian closed. So they do have exponential objects. And you can prove that so a Resk space has an underlying quasi-category, and you can prove that the underlying quasi-category of this exponential is going to recover the functor quasi-category. So I mean, there's also some sense in which these models are all equivalent in a notion that's appropriate for a change of model functor between infinity cosmoi. So right. So let me just say, no, there's no reason to make that choice if you have reason to prefer another one. So it's more sort of a technical convenience to simplify some proofs, but it's not essential in any way. Yeah.
Thank you.
Yeah.
Hello, can I ask?
Please.
So just to make sure I understand correctly, the infinity category type theory was modeled after a specific model, right? You looked at the specific model.
That's right.
Okay. So to what extent, or is this something that you don't really care about, or does it not make sense? Does that type theory interpret into any infinity cosmos? So is it possible to give a model of that type theory in any infinity cosmos, or do you need extra stuff?
Right. So Mike, who I think is here, has thought more about other models in which his simplicial type theory really would interpret. So maybe I'll defer that question to him, but I don't know of any other infinity cosmoi that interact with the simplicial type theory aside from rest spaces. And I think part of it is just, it's really hard to model homotopy type theory. You know, the simplicial layer is maybe not so big an ask beyond just having a model of type theory, but right. Mike, do you want to add anything if you're still here? Maybe not, but I should say this also isn't a question that I've particularly explored. So, I mean, it is possible there are other models, but it's not clear to me what they would be.
So can I, maybe another way of thinking of the motivation for the question is, if you take an infinity cosmos and you take just the infinity groupoids in that infinity cosmos, which I'm guessing you can define in terms of the infinity cosmos structure,
That's
right?
right. That's right.
Would these potentially be a model of hot, of just, you know, normal hot? I mean, that's really what is the kind of the motivation behind the question, because that I think would be very interesting.
Yeah, I mean, there's something kind of funny about the way the RESC space model works, in that the types are a superset of the infinity one categories rather than a subset of the infinity one categories. I mean, you know, so when you probe the internal categorical structure of a type, certain types are Siegel and then certain types are RESC. And then you're right, certain RESC types are discrete, which kind of reflect back this infinity category structure. But I mean, there's something sort of funny going on there. So that's a tangent to the question you asked. And you know, I've never proven a theorem that such and such is a model of homotopy type theory. So all I know is it seems to be really hard. So, oh, and we haven't axiomatized anything like the existence of a universe. So, I mean, you might happen to find, I mean, if you want a univalent universe as a discrete object in an infinity cosmos, I mean, that's sort of something special you'd have to find in a particular case. It's not, you know, our axiomatization is really not meant to be comprehensive. You know, we haven't sort of axiomatized all of the properties that are true of quasi-categories, for instance. You know, rather it's meant to be sort of a relatively, I mean, part of the reason it's so easy to produce infinity cosmos is we really don't ask for very much in the axioms. It's sort of something that you can get off the ground quickly and seems to be sort of sufficient to prove a lot of theorems in basic category theory. You know, maybe not all of the theorems that you want, but, you know, some subset. You know. But yeah, it's really an auxiliary notion. It's not, I mean, we gave it kind of a fancy name because, you know, why not? But it's more an auxiliary notion for developing the theory of infinity categories up to some point, and then at some point you'll probably leave the infinity cosmos and use analytical techniques or techniques that aren't in its purview. So.
I've got a question, Emily, related to what you were just talking about. So the examples of infinity cosmoi that you told us were all equivalent in some sense.
Yes.
But that's not true in general, right? I assume you could have infinity cosmoi that were not equivalent as well, right?
Yeah, that's right. So the infinity cosmoi I mentioned all have objects that are known equivalent models of infinity one categories. And there is sort of a change of model theorem that says that anything you prove in RESC spaces will also be true for quasi-categories by passing across the equivalences that you're well aware of. So that's good. But an infinity cosmos, there are other infinity cosmoi whose objects are more exotic. So the simplest thing to say is that if I take any infinity cosmos, like RESC spaces, and I take any object in it, and then I look at the isofibrations over that object, that is again an infinity cosmos. So there are sliced versions of infinity cosmoi. And I can also put additional adjectives on those isofibrations. So there's a notion of Cartesian fibration, which is meant to model functors from the base infinity base infinity category valued in infinity 1 categories. For any object in any infinity cosmos, there's an infinity cosmos of Cartesian fibrations over that object. There's also an infinity cosmos of two-sided fibrations between a pair of objects. So these are ones that are covariant in one variable and contravariant in another variable. And then there are also infinity cosmoi that model higher categories. So n complicial sets is a model of infinity n categories. There's an infinity cosmos for that, or for all complicial sets, there's an infinity cosmos for Resks theta n spaces, which is another model of infinity n. I just learned that Quasi n categories, which are Dimitri Ara, maybe with collaborators, model of infinity n categories, also form an infinity cosmos. We haven't really explored much about these infinity cosmoi, and again, we don't expect the axioms to be sufficient to prove all of the theorems that you would want to about infinity n categories, but again, they'll get you sort of some way off the ground, and then, then presumably you could just add more axioms to better reflect that situation. So,
Does anybody have questions or comments that address some of Emily's discussion points? So someone just started to talk.
Yeah, I had a question. It's kind of speculative, but it's another way of doing synthetic infinity category theory. An idea would be to do some kind of directed type theory. And people have been thinking about this. And have you thought about the relations between that and what the two models you have been discussing? And perhaps also a notion of infinity 2 topos, if that has been developed. I don't know how well that has been established yet.
mm-hmm. Right. So no, the short answer is no, I haven't thought about interactions with directed type theory. So Dan Licata, who I know is here, I should apologize. I haven't even read all the way through the email that you sent me earlier this week, but that's what I'm going to do this afternoon, I promise. So yeah, I think Dan and collaborators have been thinking about that, and I know he has something very interesting to say because he wrote me a long message that I haven't responded to. So maybe Dan can jump in after this. I mean, there is something like an infinity 2 topos structure on the infinity cosmos of quasi categories. Dom and I are working on that in one of our sort of papers in the pipeline, but I don't know, I mean, exactly what that definition is. We're sort of modeling it after this 2 topos paper of Mark Weber. Yeah, open question. So please explore, yeah.
Dan?
I don't really have that much to add to that, but I think, like, from my point of view, the simplicial type theory is a directed type theory. Like, I don't entirely understand asking about a relation there. It seems like one kind of choice about directed type theory is whether you want to pick out the covariant fibrations or the Siegel types or something like that from within a type theory of things that aren't those, or whether you want the type theory to have some modalities or something like that, such that everything you can define sort of intrinsically is a something good. And this seems like a nice approach for one of those. And then I think people haven't really thought or really successfully explored the other one or gotten as far with the other one, which maybe suggests that this is the right one.
So, I mean, I have a question, I guess, if I can jump in. I mean, I'm pretty new to synthetic mathematics. I mean, does anyone have other sort of experiences in developing the synthetic theory of some other sort of mathematical object, either in and outside of? Well, I mean, of course, in homotopy type theory, a lot of you do. But I mean, I'm sort of interested on this question that I tacked onto the abstract about what are the merits and drawbacks of, sort of synthetic mathematics as is classically understood versus synthetic mathematics that's also then in a homotopy type theory or type theory framework. Does anyone want to comment on that?
or on any other related topic?
Sure. Right. Yeah, I didn't mean to.
Well, I'll give people one more chance, but and if there aren't more comments, then we'll wrap it up. So last chance. Okay, well.
Can I just say something?
Oh, perfect. Go ahead.
So, but just as a clarification, what do we understand by a synthetic theory of something? Is it the approach of axiomatizing the collection of all things that we want to study rather than describing one such thing? Is this what really the distinction amounts to?
Yeah, I think so. Yeah.
That's it. I have nothing.
I mean, in some sense, like that's kind of how, you know, maybe this idea of synthetic theories is not so different from sort of abstraction, you know, more generally in mathematics, like, you know, group theory is some sort of synthetic theory of symmetry or something, you know. But I mean, there seems to be something different about doing mathematics in homotopy type theory that I don't know if I really have my finger on yet.
I think that's a really good question. I absolutely don't have an answer, but I'm just curious what people think about if you were to say, if someone were to tell you something is a synthetic theory versus an axiomatic theory, would that mean anything different? Or is it just another way of saying the same thing? Because, you know, axiomatic theories go back a century plus, right? So earlier. But when people say synthetic, it seems to have this feeling like you're doing something different, or at least that's what people take away from it.
I mean, a synthetic theory is also an axiomatic theory just of the collection of all the things rather than of one such thing, right? I mean, in some sense, I think isn't that essentially the distinction? So it's the trade-off between, if you're doing things synthetically, you get less structure because you can't speak of the properties of the one specific thing, but you get more models, something like that, I suppose.
But that's historically what axiomatic theories did to begin with. So.
No, but I'm saying, like, I mean, in some sense, this, for example, Emily and Mike's type theory is an axiomatic theory, right? It just axiomatizes a collection of objects rather than a single object.
Right. So both of the approaches are really modeling the category of infinity categories, either modeled as quasi categories or modeled as rest spaces. Yeah, I mean, that is an interesting observation.
I have one suggestion that just hit me actually, which is that in a synthetic theory, when people say it, typically what they mean is that they're beginning with some existing sort of axiomatized logical system or something in which they're introducing one new thing. Whereas historically, I think when you say you're axiomatizing something, you proceed to give all the axioms, whereas a synthetic theory often is, you know, we introduce some new component into an existing set of rules, and that sort of creates a new object, right, or a new class of objects. But I don't know, so I'll shut up.
I was wondering how is a proposition?
We can't hear you very well.
So let me try.
I can't hear anything. Is there a problem with your microphone?
Okay, is this any better? Can you hear me now?
Yep, that's good.
That's a bit better. Okay. I think one difference has a little bit to do with how the thing about how in type theory logic is inside the theory rather than outside the theory as it is in set theory. So when we say something like an axiomatic theory of something, then often what that means is that you're formulating axioms inside of an external sort of set theory or first order logic. Whereas sort of the type theoretic synthetic approach, we're giving rules for a theory which doesn't require an ambient superstructure of logic. I'm not sure how important that is, but I think it's maybe one slight difference.
Mike, do you have any other comments? So.
I missed some of the discussion because I'm having issues with my battery and my speaker, but I guess no, not really. It's a nice talk. Thanks.
Okay, let me give one more question, and then since we still have time and we're all gathered here, does any of this shed any light on whether it's possible to define the type of infinity categories inside the ordinary type theory?
I think no. So, I mean, we sort of put simplices as a new layer in the type theory, and that's how we're getting around this problem of, infinite objects or something. So I think no, but maybe I just don't see it. So.
The reason I'm asking that there might be something like that is if you had a good theory of infinity 2 toposes or something like that, and you knew that if you cut down to the discrete objects, there could be many different infinity 2 topos extensions of an infinity 1 topos. That would give an indication that there's not really a good theory of the corresponding infinity categories inside an infinity 1 topos. But maybe that's, is that confused or is that helpful?
Yeah, I didn't follow any of that. But something else that occurs to me to say, there's some sort of semantic property of rest spaces that is also what allowed this to get off the ground. And I think Riehl was one of the first people who had this observation. So there's a way to characterize internally to the category of bisimplicial sets when a reedy fibrant thing has the Siegel condition. That's so that usually the Siegel condition for a reedy fibrant bisimplicial set is an infinite list of maps that need to be equivalences, and those maps are actually maps of simplicial sets, so in some other context, but that's not the point. But there's a sort of internal characterization that says that a reedy fibrant simplicial set is Siegel sort of if and only if one map, which is induced by the inclusion of the 2-1 horn into the 2 simplex. If some induced map is not just a fibration, but a trivial fibration, then binary composites exist uniquely or something. And that encapsulates all the higher dimensional Siegel conditions somehow. So, right, so that's really what allowed us to try and then axiomatize or develop a type theory that reflects those particular semantics, as we had some in a particular model, finite characterization of the types of objects the class of objects that we were hoping to study. So if you want to rephrase what you, your comment and try again, please, but.
Okay, let me try one more time. So you were looking at Mark Weber's proposed definition of 2 toposes and trying to give an infinity 2 topos explanation. I'm sorry, I'm going a bit off of what is in the paper into wild speculation, because that's what we can do here in these discussions. But suppose for infinity 1 toposes, you have a bunch of truncation operations. You can truncate down to look at just the sets. You get a 1 topos. I imagine that in an infinity 2 topos, you could also just cut down to the discrete objects, and you would get an infinity 1 topos. And so in the hierarchy of infinity 1 toposes, there's this phenomenon that if you have an underlying 1 topos, but given a 1 topos, there might be many different infinity 1 toposes that have the same underlying 1 topos. So is it known, or is it conjectured, is it guessed that if we look at an infinity 1 topos, is there a unique infinity 2 topos sitting over it, or is there a choice?
I have absolutely no idea, but it would surprise me, but I have absolutely no idea.
I think there is definitely a choice. I think there's definitely a choice, but I think that there's also going to be sort of a canonical one that you're going to get by building basically res objects in your Infinity One topos.
Okay, well, I think time's just about up. So why don't we all thank Emily again?
And thanks to the organizers for putting this together. I mean, this is a great initiative. I hope we continue to do it in future semesters. So I'd love to hear many of you give talks. So yeah.
Thank you. I will just remind everyone that in 2 weeks we have Carlo and Julie, who's going to speak on the computational semantics of Cartesian cubical type theory. And I will check with Emily after, but if she agrees, then this talk will also be posted with a link from the Hottest website. Okay, thanks very much for attending.